Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In our discussion today, we're going to look at the concept of entropy change at constant pressure and constant volume. And in our various discussion on the various aspects of enthalpy, entropy, and some aspect of molar heat capacity, where we had used the various variables of temperature, pressure, and volume. And I mentioned that basically trying to fix or creating one of the variables or two of the variables constant, and therefore we're going to see that the third variable is going to be fixed automatically. So in our discussion today, we're going to look at the two variables for pressure and volume, and try to see how we can be able to represent this aspect of entropy in that specific order. So in this particular case, then therefore we're going to look at the two representations that we have done for representing the heat at constant the molar heat capacity at constant pressure and the volume. And I'd said that we can be able to represent the heat involved in this particular case in terms of sigma Q. So we're going to have this one, sigma Q, at constant pressure using that subscript there. And this is equivalent to, we had given that is molar heat capacity at constant pressure, and then we had given it with the dt given as such. So this is the equation that we had given for representing the heat that is going to be involved in this particular case at constant pressure. So similarly, we had said that we can be able to represent the heat that is going to be involved at constant volume using that subscript for phi. And of course, this is going to be given as Cv, which is the molar heat capacity at constant volume, and then dt given as such. So, and then we had mentioned that we are going to represent enthalpy, which is the ratio between the heat capacity over the temperature that is going to be involved in this particular case. And therefore, involving this particular aspect of constant pressure and volume is going to give us the specific equations that we need to represent this particular aspect of entropy. Therefore, in this specific case sense, I'll consider this relationship between these two specific equations. And we had said, of course, for us to derive this aspect of entropy from the two equations, we are basically going to divide these particular equations by absolute temperature. So this is the first one and the second one. So therefore, for me to have a derivative of this specific entropy at constant pressure, I'm going to have this one divided by this specific in order for me to have a ratio of delta S given as such. So therefore, I'm going to give the first representation of this specific case for change in entropy at constant pressure, which definitely is going to be given. So I'm going to do it in this specific order. So we are going to have so we're going to be able to represent change as dsp, of course, which is the change in entropy at constant pressure given as such, which is going to be the ratio between, as I said, delta qp all over t given as such. So this is going to form our first equation, and then we're going to have the change in entropy at constant volume represented using the delta q v all over. So basically, this is going to be given as a sigma, not delta. So the delta is given basically as this one. So this is going to be sigma qp over t, and this is sigma qv over t given as such. So definitely, then therefore, this is going to be a sigma over t. Just a minute, there's something I want to confirm. So this is going to be sigma qv over t. Then this is going to imply that we are going to have this, of course I'm going to give, okay, let's consider this one as equation 2. Then if we try to look at this, and this specific case we had given this particular representation for entropy at constant pressure. So this is going to be Q, the sigma Qp over T, which is basically equivalent to this particular equation all over t. So there's an element of dt that we're going to see being involved in this particular case. So this first equation that therefore is going to be represented using that specific element of c P, which is a molar heat capacity at constant pressure. Therefore, my equation 1 is going to be given as dSP sigma QP over T dt, which basically is this specific element. So in order for us to derive this specific equation for entropy change at constant pressure, we are going to divide by T. And as we said, of course, this therefore is going to be the product over this specific 2. So I've divided by 2 on both sides in order for me to achieve this specific relationship. And then next we are going to see that for the second case, for the entropy change and the constant volume, we're going to have the ratio between this specific Q. This is going to be sigma QV over T, and this sigma QV over T is going to be represented as CV dt over T given as such. So therefore, this is going to be the derivative that we're going to obtain, whereby basically this specific numerator is the product of this particular ratios that we have given as such. So therefore, from the second case, we're going to see that sigma QV is equals CV dt, which is our numerator, and then we're going to divide it by T in order for us to get the ratio for entropy. So that's how we're going to perform various of course, variations for these different aspects of a constant temperature and pressure, and perhaps we can be able to just do this one in terms of the integral form. So we're going to look for a scenario whereby we're going to have a change in temperature. So for the constant pressure, we're going to have a change in temperature. So we have said that we're going to give the change in entropy at constant pressure given as such, which of course we have said that it's going to be given as a Cp dt over T. So for us to find this specific value, we're going to have this one done over an integral over the variation in temperature. So let's say the temperature is from T1 to T2. So for us to find this specific value, then therefore we're going to do an integral between T1 and T2. Therefore, this is going to be given in terms of an equation, which is going to be, so this is a constant which we're going to see. So in terms of our integrals, this is going to be Cp, the integral between T1 and T2, and then this is going to be given as dt over T. So for us to perform this one and find an evaluation for that, we're going to take this particular change in temperature as the natural logarithm of T1 and T2. Therefore, this is going to be represented as Cp, the natural log over T2 over T1 given as such, and that is going to represent change in entropy at constant pressure, which is going to be illustrated using this specific formula. So in that particular case, we can be able to consider the aspect of a mole, whereby we're going to see that for a mole, of course, this is going to be given in terms of the ideal gas equation, which is PV nRT. So for that case, we're going to see that in cases whereby we're going to have a constant volume, we're going to see that there's going to be variations in what we refer to as pressure, and therefore we're going to have a different kind of representation in that specific case. So therefore we're going to see that under constant pressure, this is going to be the basic representation that we're going to have for that. So similarly for volume, we can be able, so I'm going to just leave this one for another discussion. So this is for the representation of entropy change at constant pressure given as such. So similarly for volume, we're going to have the change in entropy is represented as the change from V1 to V2. So this is going to be T1 to T2. Of course, that is under constant volume. So there's going to be change in temperature, and this is a molar heat capacity at constant volume, and then dt over T given as such from the various ratios that we've discussed. So this is going to be given as Cp, the integral between T1 and T2, dt over T given as such. So therefore, similarly, we're going to represent, to have this specific representation given as Cv, a natural log over T2 over T1. Just a similar case for this specific so therefore, for the sake of space, I'm just going to leave this one. But in this case, the evaluation of this specific integral is going to give me Cv natural log over T1 over T2, to represent the molar heat capacity and the entropy change at constant volume, that respect case, and then the molar heat or the entropy change at constant pressure given as such. So I hope the two formulae are going to assist us in trying to evaluate the question set that we're going to use in various discussions in this specific concept of entropy. And kindly check our description boxes for various links of other videos which are going to be similar to this. So that is it for now, guys. Bye. God bless you. Catch us in our next video.